If you have a mountain of trash, generating electricity from it seems as simple as throwing it all into a massive fire. But feeding unverified random waste into a modern boiler is risky. Without knowing the exact composition of the fuel, operators can melt the plant's internal infrastructure in months or trigger a toxic emissions crisis. Safe power generation requires treating a city's waste as a complex, volatile chemical compound. Before a single bag of trash enters the furnace, engineers run a series of tests to extract its unique chemical profile. This report for a landfill sample tracks primary energy markers: moisture, ash, and carbon. These percentages dictate the raw heat produced. Further down, the chloride concentration becomes the focus. This value determines how quickly the plant's internal piping will succumb to corrosion. The metal analysis adds a layer of safety data. By tracking the total threshold limit of elements like lead, engineers can predict the environmental impact of the exhaust gas and the leftover ash. These values provide a roadmap, allowing operators to calculate exactly how the fuel will behave once it is ignited. The core fuels creating heat in the furnace are carbon and hydrogen. Their primary efficiency drain is moisture. Fresh municipal solid waste typically arrives with a moisture content exceeding 44%. Because energy must first be spent boiling off that water, it is a relatively weak fuel source. Excavated landfill waste is much drier. This chart compares their lower heating value, or LHV. While fresh waste produces about 4,600 kilojoules per kilogram, the dry landfill material reaches over 11,700, nearly tripling the potential heat energy. This energy density is a major advantage for power output, but it introduces a physical limit on how hot the boiler can safely run. The risk is tied to chlorine. The high energy in landfill waste is often a result of discarded plastics, like PVC, which are saturated with chloride. At extreme temperatures, chlorine becomes hydrochloric acid gas, quickly pitting and thinning the boiler's metallic water pipes. To prevent rapid structural failure, engineers set a hard thermal cap. By keeping live steam at 415 degrees Celsius, they slow the reaction, keeping the plant operational. Operators must also monitor the ash. If the furnace exceeds 1150 degrees Celsius, the unburned residue hits its softening point and melts into a sticky slag that clogs the internal systems. Engineers have to maintain a fire that is hot enough to generate electricity, but cool enough to prevent the fuel from destroying the machine. While fire destroys organic matter, elements like sulfur, nitrogen, and heavy metals remain in the ash. High-temperature combustion concentrates these metals in the bottom ash. This report shows high total concentrations of barium and lead in the landfill sample. To ensure long-term safety, engineers use the STLC test, simulating acid rain to see if metals leach into soil. As these results demonstrate, leachable amounts of barium and lead stay well below legal limits, meaning the ash can be safely managed. These specific lab values serve as the data-driven safeguard between industrial operations and the local ecosystem. Fresh municipal waste is too wet for high efficiency, and dry landfill waste is too corrosive to be used in isolation. To solve this, engineers blend waste streams on a massive scale for a stabilized hybrid fuel. By mixing 74.8% fresh waste with 25.2% dry fuel, operators dilute the corrosive chlorine while boosting energy output to a sustainable 6,400 kilojoules. The plant's efficiency isn't decided in the furnace, it's locked in hours earlier during this stabilization process. The numbers on a lab report provide the control needed to manage the chaotic nature of municipal waste. These facilities operate as high-precision chemical plants. They decode the profile of a city's waste to extract steady, predictable electricity.